The principle of how electricity makes a motor move is closely related to the phenomenon of electromagnetic induction in physics. This principle begins with the basic concept that an electric current flowing through a conductor creates a magnetic field around it. This magnetic field changes depending on the magnitude and direction of the current flowing through the conductor, which in turn allows the electric motor to perform rotational motion. Let's dive deeper into this process step by step. 1. Electromagnetic induction. The fundamental principle of a motor is based on the phenomenon of electromagnetic induction, discovered by Michael Faraday. Faraday found that when an electric current flows through a conductor placed in a magnetic field, a force is exerted on the conductor. This force is known as the Lorentz force, and it occurs when an electric current flows through a conductor within a magnetic field, causing the conductor to move. The direction of this force is perpendicular to both the current and the magnetic field, which can be determined using the right-hand rule. 2. Basic structure of an electric motor. An electric motor consists of two main components, the stator and the rotor. The stator is the stationary part, typically containing strong permanent magnets or electromagnets that create the magnetic field. The rotor is the part that rotates within the magnetic field of the stator and contains a coil of wire through which current flows. When current flows through the rotor, the magnetic field of the stator exerts a Lorentz force on the rotor, causing it to rotate. 3. Brushes and commutator. In a DC motor, the direction of the current must be continuously reversed to maintain a constant rotational direction of the rotor. This is achieved through the use of brushes and a commutator. The brushes connect the external power source to the commutator, which reverses the direction of the current depending on the rotor's position. This allows the rotor to continue rotating in the same direction. On the other hand, in an AC motor, the current direction changes periodically by itself, so brushes and a commutator are not needed. 4. Current and rotational speed. The speed and torque of the motor are determined by the amount of current flowing through the rotor and the strength of the magnetic field created by the stator. The greater the current, meaning more charge carriers are moving, the stronger the Lorentz force generated, which increases the motor's rotational speed and torque. Additionally, the stronger the magnetic field of the stator, the greater the force that can be generated with the same current. Therefore, the motor's output and efficiency are greatly influenced by the current, the strength of the magnetic field, and the structure of the rotor. 5. Types of motors and their characteristics. There are various types of motors, each optimized for specific applications. For example, DC motors allow precise speed control and have high torque, making them popular in robotics and power tools. In contrast, AC motors are simpler in structure, require less maintenance, and are commonly used in industrial machinery and household appliances. Recently, BLDC motors, brushless DC motors, have gained attention, as they do not have brushes and commutators, resulting in lower friction losses, longer lifespan, and reduced noise. These motors are widely used in advanced technologies such as drones and electric vehicles. 6. Efficiency and heat dissipation in motors. When a motor operates, some of the energy is converted into heat, leading to heat dissipation. This heat reduces the motor's efficiency, with a significant portion of it being generated by the resistance to the current flow, Joule heating. This heat accumulates inside the motor, which can affect its performance. Therefore, solving the heat dissipation problem is crucial for designing high-efficiency motors, which involves careful selection of materials, structural design, and cooling systems. 7. Future of motor technology. Although motor technology has advanced significantly, there is still room for improvement. For example, developing stronger and lighter magnets or using conductive materials that can withstand higher currents can enhance motor performance. Moreover, integrating smart motor systems with artificial intelligence can enable more precise control and energy efficiency. As motors play an increasingly important role in various fields, such as electric vehicles, drones, and robotics, advancements in motor technology are expected to bring about significant changes across industries. In summary, the principle of how electricity makes a motor move is a complex process that combines various principles of physics and engineering. By understanding and applying these principles, we can utilize motors in diverse ways, further advancing modern civilization.